The concept of molecular orbital was brought forward by Hunt and Mulliken, and using the molecular orbital theory, they were able to explain the chemical bonding and structure of different homoatomic and heteroatomic molecules. The basic concept of molecular orbital theory derives. Now we have to think about the formation of molecular orbital from atomic orbitals. So, to explain the formation of molecular orbital from atomic orbitals, we use a simple concept, and the concept is called linear combination of atomic orbitals. It is called LCAO, linear combination of atomic orbitals. So, LCAO says that combination of atomic orbitals take place by the addition or subtraction of wave function. So, by the addition and subtraction of wave function psi, molecular orbitals are formed. So, the formation of molecular orbital is based on the wave function and its addition and subtraction. Now see here, we have to see how the wave functions overlap by addition and what is its result. Now see here, when now we have to see what will be the effect of subtraction of individual wave function and how it affect the formation of molecular orbital. So now we are considering the molecular orbital formation from oneness orbitals. We know oneness orbital is the first orbital of any atom and they have spherical shape. So an oneness orbital same thing will happen for 2py orbitals. 2py orbitals undergoes constructive overlap to form. Now see here, we have created many molecular orbitals. According to MO theory, electrons are present in the molecular orbital in a molecule. So we have to fill the electrons in these molecular orbitals. When we have to fill electrons in these molecular orbitals, we have to consider three important rules. They are Aufbau principle, Pauli's exclusion principle and Hund's rule of maximum multiplicity. Aufbau principle states that electrons are entered into the orbitals. Here the reference is molecular orbital. So we could say electrons are entered into the molecular orbitals in the increasing order of their energy. That means the first electron will go to the molecular orbital having minimum energy, while the last electron will go to the orbital having maximum energy. The second rule is Pauli's exclusion principle, and we know the significance of Pauli's exclusion principle is that an orbital can accommodate a maximum of 2 electrons. For any orbital, the maximum limit is 2 electrons, whether it is an atomic orbital or a molecular orbital. And the third rule is Hund's rule of maximum multiplicity, which states that pairing of electrons could only occur till all the available orbitals are half filled. If two orbitals are having same energy, then electrons has to be distributed uniformly till half filled. Then only pairing could be possible. Now, obeying these three rules, we have to fill the electrons in the molecular orbitals. Now we will see the molecular orbital picture for diatomic molecules up to nitrogen molecule with atomic number 7. Nitrogen is having atomic number 7. So two nitrogen molecule combines to form two nitrogen atoms combine to form nitrogen molecule. So the configuration I am showing here, or the MO picture I am showing here, is only up to nitrogen, because in case of p orbitals the configurations will change depending upon the molecule. See here, this is the MO picture of molecules till nitrogen. See here, I haven't drawn, there is no 1s orbital, that you have to draw. First, below this 2s there is an 1s orbital. The 1s orbital combine with another 1s orbital to form sigma 1s and sigma star 1s. So among the molecular orbitals, the minimum energy is to sigma 1s, and this configuration is only up to nitrogen molecule. I told you the p overlapping of p orbitals to form molecular orbital will change with molecules. For 1s and 2s there is no change, but for p orbital there will be change. See here, this is the configuration up to nitrogen molecule. So I could write the configuration is sigma 1s minimum energy, or the molecular orbital with the minimum energy is sigma 1s, then sigma star 1s, then sigma 2s, then sigma star 2s, then pi 2px having same energy with pi 2py, then we have sigma 2pz, then pi star 2py having same energy with pi star 2px, and finally sigma star 2pz. So this is the molecular orbital picture for any molecule up to nitrogen, and the order, increasing order of their molecular